Okay, good afternoon, everyone. To this afternoon session, we have lined up a few talks which are going to be very interesting. So our first speaker in the afternoon session is Professor Jörg Wrachtrup from the University of Stuttgart and Max Planck Institute for Solid State Research. He's been really the pioneer in research on NV centers in diamond and especially on nanoscale quantum sensing. And it's my great privilege to welcome him to give this introductory first talk. And also he'll follow up with another talk on Wednesday. Professor Wrachtrup, the floor is all yours.
All right, yeah, thank you very much for the kind words of introduction. I trust you can hear me and see my slides well. I would like to apologize, first of all, not being able to be on site, but we have some arrangements in the university presidency in which I'm involved in that happened on short-term notice, which forces me actually to be in Stuttgart. We share somehow the tropical temperatures you might have in Bengaluru. So for us, it's quite unusual to have something like above 35 degrees. And yesterday it was actually 38 degrees, which gives us a, you know, kind of at least a feeling on how it is in summer in your place. Anyway, so what I would like to talk about today and next lecture is about our experiments in quantum sensing, specifically quantum sensing on very short length scales, because that is the strength of the physical systems we are working with. My name is Jörg Wrachtrup. I'm working here as a director of the Center for Applied Quantum Science at University of Stuttgart, and I'm co-affiliated with the Max Planck Institute for Solid State Research, which is here our next neighbor building. So what you see here already on the first slide is a mock-up of the type of sensors we often work with. What you see here is this reddish blob. Actually, in this blob there is a micron-sized diamond, which is doped. This is why it generates red fluorescence. If you excite it with a green laser, like 532 nanometer, and that's what you see here. This is a fiber onto which we have glued this nanodiamond. And essentially, the sensing we are doing relies or depends on that we detect the intensity changes in this red fluorescence. And this is what is the observable in our experiment. Now, this is micron size, so that you can make a nice photograph of it. And we operate these sensors from millimeter type of sizes down to a few nanometers. And I'm going to show you what the specific features of these sensors are. Of course, the physical basis is very much similar to other kind of precision measurements you already might have heard about in metrology. Very well. To give you an idea on actually what the physical basis of the sensor material is we are working with. So we are working with solids as a sensor medium that is not atoms and gases, but structures where you would characterize their physical behavior by a band-like energy level diagram, and that's what you see here. So the bottom and the top part of the figure, VB and CB stands for valence band and for conduction band. There is in solids a sizable band gap in between valence and conduction band. In the case of the materials we work with, this band gap is on the order of a few electron volts. One of our most used solid diamond has a band gap of 5.5 electron volts, so that's deep into UV, right, around 200 nanometer or so, meter-ish type of wavelength would be necessary actually to excite charge carriers electrons from the valence to the conduction band. If you dope that material, then you can generate optical, then you can generate two-level systems, that is isolated energy levels within the band gap of that material. For the dopants, we use typically the energy separation between ground and first excited state are on the order of an electron volt. That is, optical transition lie at around 600 nanometers or so. And we choose systems where we have a strong optical dipole transition. So very much like we have it in lots of atoms people use for atom vapor magnetometers or optical clocks. And this optics is our sensor readout. This is how we initialize our sensors. And this is also what determines the signal to noise in sensing. And we always try to go down to short noise limit, at least for the precision we reach in measurements here. But the sensor levels by themselves are spin levels. So we seek for systems where we have unpaired electron spins. So that, for example, we have for a spin 1/2 system, the two energy levels would, in an external magnetic field, would split. And we also look for systems for dopants where we can read out the energy separation here between these two levels with exquisite precision. And in solids, that means you go down to a precision or an inaccuracy in the splitting here, which is on the order of a few femtoelectron volts. This would mean that we can determine the frequency with hertz, between hertz and millihertz, a kind of frequency resolution. Or if you are more into wave numbers, this would mean that we could read them out with 10 to the minus 10 wave, 10 reciprocal centimeters. And these are the levels we use for sensors. Very often, technically, this involves driving spin transitions here by microwaves and reading out the response optically. The material we are working with are wide bandgap semiconductors or insulators. The prototypical material in which we started to work with is diamond. Diamond, and I will come to that in a minute or so, has a couple of properties which allow us to really reach this level in precision in reading out between these two electron spin sublevels. Silicon carbide also belongs to that family. It's a mixture between carbon material, that is diamond, and silicon, and inherits interesting properties from both of the constituents, once again allowing this exquisite precision, at least for solid state systems, very good precision in reading out the spin sublevels, energy difference. All right. So just to give you an overview of what kind of, problems and areas of science we are working in with these kind of sensors. On the one hand, quantum networks here, this is a wrong wording, but what we use them for to make material science in modern electronic materials, as you know, and I will give you an example. 2D materials have very interesting electronic, but also magnetic properties, and we use our sensors to read out these properties with high spatial resolution. Because the sensor material retains its excellent quantum coherent properties even at room temperature, one can use this for biomedical analysis. And what you see here on the top right corner is an example of an experimental study where people have used a mice and have injected nanodiamonds, that is diamonds with a dimension smaller than 100 nanometer into the mice. The different color here comes from the fact that these nanodiamonds contain different dopants. The chemical nature of the dopants is different. As a result, the absorption and emission properties are different. And this is then indicated by the different emission colors you see here. On top of that, in this study, these nanodiamonds were coated with a specific surface chemistry, that is molecules on the surface of the nanodiamond, which target or which lead to the fact that the nanodiamonds localize at different parts in the body. And this is used here. And on top of, just indicating the location of a specific chemistry going on in the body, because of the spin nature of the dopants, you can also use them to analyze the chemical composition in the environment of the nanodiamond. And one way to do this is nuclear magnetic resonance. And in the course of the talk, I will show you how to combine nuclear magnetic resonance with the kind of quantum sensing we are doing. In a different study, people use the fact that one can very easily measure local magnetic fields with these kind of sensors to actually explore and image nanomagnetic features. Once again, nanomagnetism is a very timely and intensively researched area in modern solid-state science, because magnetic features are getting smaller and smaller because, for example, people want to use them for highly integrated data storage devices, but physical chemical tools actually to characterize these magnetic nanostructures are getting rare at these dimensions where structure sizes are below 100 nanometers. It turns out that these kind of quantum sensing we are doing is almost ideally suited to look into these systems. I'll give you one example this time, and then a more extended introduction on Wednesday into how and what one can do with that. And last but not least, the type of sensors we are producing have made their way into industry and industrial products. And one example is that companies like Seagate and Toshiba are investigating their hard disk drives, specifically the right head of the hard disk drives with our sensors. So, as you probably know, it is still so that for cheap storage, hard disk drives are the solution people use, but also their storage density is increasing, which means that the feature sizes one needs to write into the writing medium is getting smaller and smaller, and the devices, the technical means by which these feature sizes are written are these hard disk write heads, which are getting smaller and smaller. And these industries were just looking for characterization tools which would allow them actually to measure the magnetic field being produced by their write heads. And we and others were coming up with solutions which are now used in the research lab of Seagate and Toshiba and are commercialized by vendors catering actually characterization equipment to those industries. All right. Now the next step is what are actually the sensor materials we are working with. So what are the materials people use to dope and then to use nanoscale quantum sensing? And one material where all of this started with certainly is diamond, and I'm going to show you a couple of examples of nano quantum sensors from diamond. Rare earth dopants like cerium, praseodymium, europium, erbium, also transition metal ions. In certain host systems like yttrium, aluminum, garnet, but also other silicates are actually pretty good nanoscale quantum sensors. They're also good qubits for quantum memories, but you can also use them for sensing on small length scale. And then silicon carbide, I was mentioning that material already, shares a lot of similarities with diamond. On the other hand, it is also a material which is used in electronics industry, high power electronics. So technically it's a bit more mature than diamond. And these days, lots of people are investigating or are developing products and devices for solid state based quantum sensing out of silicon carbide. But by large, these are the three types of systems we and others are working with. All right, so now let's specifically look into one system, which is well, probably one of the most well-known systems, and this is nitrogen vacancy center in diamond. Now, diamond, and that you probably know, is a carbon material. It's an all-carbon material. Every carbon atom is surrounded by 4 next nearest neighbors. It's covalently bound, and this gives it typical physical properties because of the light mass and the strong covalent bonding. On the one hand, all lattice vibrations occurring at very high temperature, and characteristic for that is what we call Debye temperature. This is a measure for the cutoff frequency of optical phonons, and this is 2000 Kelvin, which essentially means that below these temperatures, a lot of optical phonons, that is short wavelength lattice vibrations, are non-existent. And that in turn means that as phonons are the #1 scatterers responsible for decoherence of all optical transitions, but also all spin transitions, that these decoherence mechanisms are very small, not very prominent, even at elevated temperatures like room temperature. Because of the light constituents, we also do have very small spin orbit coupling. So LS coupling, this lambda parameter in the Hamiltonian, is pretty small, which overall means that if you look into spin lattice relaxation of electron spins at room temperature, then the decohere or the relaxation times are on the order of milliseconds. This is probably not very long. If you look at the diluted atom gas, this easily, is seconds or longer. But if you compare it with other solids like gallium arsenide, or I could also take silicon here, then typically these spin lattice relaxation times are more like microseconds at Kelvin temperatures. And if you go to higher temperatures, which sometimes for bioapplication, for example, is what you want to do, then these times would be reduced to picoseconds. But this is not so in diamond and silicon carbide, and this is why we like to work with them. In addition, diamond, and that's also true for silicon carbide and a lot of other host materials we are working with, crystals, the lattice contains only a very few nuclear spins. So in diamond, for example, the majority isotope is carbon-12, 99%, which is nuclear spin-free, and only 1% carbon-13, which means that any kind of magnetic noise being generated in the material is very low. And even it is fairly easy to even purify the diamond to 99.9999 blah, blah, blah percent or so from carbon-13, so that you get an almost nuclear isotope, spin-bearing nuclear isotope-free lattice. And the same is true for silicon carbide, for example. And overall, this makes it a really a system where you can dope individual electron spins, and you get really, for all solid-state systems, really long spin relaxation, and in the end, also decoherence times. I'm coming to that in a second. All right, so now how actually does a typical experiment look like? The electronic ground and optically excitable first electronic state do have a delta E of around 2 electron volts. This is 640 nanometer or so of a transition wavelength. And in most cases, if you excite the system here, it returns straightforwardly by emitting fluorescence, or in solids people typically call this photoluminescence, to the ground state. The ground state, or the spin so that it's very easy to see single dopant atoms in diamond, right? So you just take an ordinary optical microscope, you record the fluorescence, you excite the system, and then you will easily see individual atoms lightening up, or dopant atoms lightening up in the system. Oh yeah, by the way, for those of you who haven't seen this nitrogen vacancy center actually comprises a nitrogen atom, which is at the carbon lattice side, and the next nearest neighbor vacancy. And the way you do this is for example, you implant nitrogen in a pure diamond, and then upon annealing, so if you heat up the crystal to 700-800 degrees or so Celsius, the nitrogen then very easily replaces the carbon, and it bonds to a neighboring vacancy. So that is a chemically very stable bond, and this is how you form this NV center in the crystal. So it's a rather straightforward way of making these defect centers, and it's very robust over a wide range of parameters like pressure, temperature, and so on and so forth. Physically, the spin state of this NV center is a spin triplet, so it's not S1/2, but S1, which means you have 3 magnetic spin sublevels. This M sub S0, +1 and -1. And by means of optical selection rule, it is this M sub S0, which is the level from which you excite the system and get fluorescence. Whereas these other spin sublevels generate dark states, that is, fluorescence intensity is way reduced if the system is, if the spin is in one of these sublevels. So, for example, if you take microwave, and you would see this is on the order of gigahertz or so, 3 gigahertz, typically our frequencies we are working with, you can actually pump the system, if you like, to one of these states, say M sub S minus, and then the fluorescence is reduced. And that's what you see here. So if we plot the fluorescence of the system as a function of microwave frequency, here this is on the order of 2.9 gigahertz. For different reasons I'm coming to, then you see that the fluorescence is reduced. So this is just a spin resonance, an electron spin resonance experiment with optical detection. And because of the long spin relaxation time, but also because there is very little magnetic noise in the environment and very little phonons being present, it is very easy, to do things like driving the system. So looking at the fluorescence intensity as a function, for example, of the interaction time of the microwaves with the spin, you see these type of oscillations, which is just like Rabi oscillations. People routinely observe in all kinds of other systems, like atoms, gases, and so on and so forth. This, by the way, is done at room temperature. Typically, the Rabi frequencies for the experts we achieve here can be up to 100 megahertz or so. And I'm commenting on the spin dephasing time in a minute or so. But this typically is how an experiment looks like. It involves optics and it involves microwaves. There are ways to do it in a microwave-free regime, but I'm not going to allude on that very much, so at least not today. All right, so now we are already approaching application cases. What I've shown here on this transparency are the applications people have done over the past couple of years. It's almost a decade, I would say, of research on that system in various areas. So on the one hand, because we have a spin, it is, of course, very easy to sense magnetic fields. You just measure the Zeeman splitting, and here you have your magnetometer. As we will see, the record values for sensitivities are on the order of a few hundred femtotesla square root of hertz. If you compare this with other magnetometers like atom vapor magnetometers, for example, then this is easily like 2 orders of magnitude less sensitive than these magnetometers are. Also, if you take a SQUID, superconducting quantum interference device, sensitivity is easily reach a femtotesla, whereas here we are pretty much limited to 200 femtotesla. So that's a limitation. On the other hand, these sensors are technically very easy to do and can be very compact, as you will see. And this is where the profit comes from. One can also measure electric fields. So although diamond and also silicon carbide contain or comprise light constituents, where you nominally would expect that spin-orbit coupling is very low, which indeed it is sufficient actually to measure an electric field shift of the Zeeman level. So you can do Stark effect type of experiments. And this is once again due to the rather long relaxation and spin decoherence time. So you see these tiny shifts. People and we have measured, so we have used it for electrometry. And just to give you an idea, we can measure the charge of a single electron spin at roughly, say, half a micron or 200 nanometer distance. So that's 10 to the minus 6 volts per centimeter at square root of Earth. If you compare this to other sensors, so record values are for electrometry, at least for solid state sensors, come from single electron transistors. So people actually use the Coulomb effect, which is tuning the start levels of single electrons in a transistor type of device. There you easily get like 4 orders of magnitude more sensitive. On the one hand, these devices are way more complex, they are way larger, they require very low temperatures to operate. All of this is not the case here. So it is fairly easy, for example, to use these devices to image the electric field in structures like this. What you see here in this small inset is actually a crosscut through a flash memory cell. Essentially, this is a condensator. There is an electric field being built throughout this insulating layer, and you can use these ND centers and defects in silicon carbide and so to image that electric field. And people are doing this actually to measure the quality of the insulating layer in this flash memory cell with spatial resolution of a few 10 nanometers. Another area of application actually is temperature measurement and force sensing. And today, if we make it to that point, I'll give you an example on how to measure temperature with this. Physically, that's very easy to see how this works. I mean, these defects and dopants, they are living in a solid. And as you know, if you put a solid if you warm it up or cool it down, the lattice constant changes, that is the average spacing between atoms changes. And this spacing actually has an impact on the spin and electronic wave function of the dopant in the lattice. And this you can measure. It also shifts the Zeeman levels. And people have made it to a precision of a few 10 microkelvin square root of Hertz, or you can measure atto-Newton forces. Once again, there may be more sensitive thermometers, and certainly you can measure forces with greater precision, but being able to do this in a compact and applicable device which solves real-world problems, this is a unique opportunity you have here. And once again, as I was saying in the last part of my talk today, I'll show you one example of application of exactly nanoscale temperature sensing. And this is a development which is a bit outside of the field we are working in here in Stuttgart. You can make nanodiamonds and nanoparticles of silicon carbide or rare earth doped solids, put your dopants inside, and then in addition to using all of these 3 sensing capabilities, you can chemically functionalize the system and give it then new sensing capabilities. For example, you can put on molecules here which sensitively react towards pH changes. And these pH changes then, for example, stretch or shrink the size of the molecule. And if you have ferromagnetic particles at the end of the molecule, this would mean that if the size here, the length, the average length of these blue things changes, the average magnetic field here at the center of the dopant of the nanocrystal where your spin is changes, and through this change in the magnetic field, you can measure indirectly pH or redox or a whole set of target chemicals. This is where people in physical chemistry these days try to make these systems very reliable and very sensitive sensors for quantities like this. And typically what you measure is either the Zeeman shift or spin relaxation. All right, so there is, once in a while you see that there are these asterisks here, and this comes from the fact that in these fields, silicon carbide has shown its superior performance over a diamond, for example. So this just to indicate you that you have a whole wealth of different materials where people really do these experiments these days. Excellent. So this would be the outline of the next, say, 40 minutes or so I have reserved for today's talk. So I'm going to show you how to measure and actually image magnetic fields. I'm going to have reserved like 5 to 10 minutes for an experiment on precision temperature measurements we did on small length scales, and then I'll have some more. I'm not sure if you have the technical capabilities actually to ask questions in between, but from my side, should there be a microphone, please raise your hand, and I'm happy to discuss questions throughout the talk. Should they come up. All right, so let's start with the first part, which is about measuring and imaging magnetic fields. Okay, so just as a start, once again, how do I measure magnetic fields? Very simple. What I've shown here are the 3 spin sublevels of this MV center, which I use here as an example. Where this middle sublevel is the one where you can generate photons from, whereas the other ones are the ones which actually where your system is rather dark. Now, we measure actually magnetic fields by driving the spin resonance. That is, we drive the spin transitions between these Zeeman levels here. And of course, if you apply a magnetic field, you then measure the Zeeman effect, and the spin splitting here is then proportional to the magnetic field. And if you assume that the mu of your electron spin is constant, which it is in our experiments, so the G factors are very constant in our experiments, then essentially you get a calibration-free measurement of magnetic field. I should say that there is some anisotropy in the system, so you have preferential alignment of the electron spin given by the crystalline lattice. So essentially you have the capability of doing vector magnetometry. That is, you can measure also the orientation of the magnetic field. All right. So this is very much as it is in atom vapor magnetometers, for example, very similar technique, except that there you would not need to use microwaves. All right. So if you put now your sensor in an inhomogeneous magnetic field, then this spin transition here would occur at different frequencies. That's what you see here on the left and the right. Right. This is the frequency axis, 2 to 4 gigahertz, and you see these dips occur at different frequencies, and you can measure these frequencies, and then the difference between nu1 and nu2 would give you actually a rather direct measurement of the magnetic field. In practice, we do these experiments through a time-dependent measurement. That is, essentially, we measure the Larmor precession of the electron spin in the external magnetic field. Well, as you know, right, the spin wave function, if you have an Hamiltonian, you want to measure actually is propagated by this Hamiltonian from a starting wave function, which in other words means the electron spin is precessing around the magnetic field with a frequency which is proportional to the magnetic field. And we run our experiment in such a way that we apply microwave pulses, which actually switch our spin state into an initial spin wave function. And at some point, we apply another microwave field. So this is a classical Rabi oscillation type of experiment where we then stop this evolution. And what we measure is the phase the spin has acquired over the measurement time small t, and the maximum time we can get here to measure phi with largest precision, at least in an experiment where we have no entanglement, no correlation whatsoever, is given by the spin dephasing time, which is on the order of 3 milliseconds or so. And then you can plug this into your sensitivity equation, which once again is rather universal throughout different types of sensors. Then this is what you get. But maybe I'm commenting a bit on this equation here. Essentially, the sensitivity is limited by T2. So T2, the dephasing time goes in as square root of T2 as long as we are scaling with the standard quantum limit. And then the other parameters here are rather constant, except the C. The C is the contrast, so that's the signal amplitude. And so what people typically fight with in these experiments is getting the contrast, the signal as large as possible, and getting this T2, the averaging time, the coherent evolution time, as long as it gets. Now, if you take a single dopant, if we take a single dopant atom, and we achieve a decoherence time of 3 milliseconds, then we have a sensitivity of on the order of nanotesla, and this is the field of a single nuclear spin at 10 nanometer distance. And I'm putting up this example because a lot of the applications actually are not bulk sensors where you have lots of these defects to actually make the signal to noise in your experiment as good as possible, but where we have single dopant atoms and we rather use the spatial resolution which comes with proximity to, for example, two magnetic dipoles. All right. So if you want to gain sensitivity, so if you want to go beyond this 10 to the minus 8, so roughly 10 nanotesla per single dopant atom, then what you can do is you can play with this C in a sense that you increase the signal to noise ratio of your sensor. Once again, this is in individual, this is in the diluted ensemble case where we have no dipole interaction between the sensor atoms or sensor dopants or any kind of other means by which we achieve entanglement. Then, of course, the C, the signal to noise scales with the square root of the number of defects you have. And like in an atom vapor magnetometer, right? It's very much, or in any kind of other atom-based, atom gas-based sensor. Okay, so what I'm plotting here is the achieved magnetic sensitivity in Tesla, right? So here we have picotesla, and down here would be femtotesla. This is a function of measurement time. So typically we calibrate everything to 1 second everything time. And this is what you achieve, or what people routinely achieve these days with these type of sensors. For ensembles of this should be a small n here, for a small n of on the order of 10 to the 10, 10 to 10 to the 12 defects or dopants, you achieve a sensitivity of 1 picotesla per square root of Earth. This greenish curve here is the recent improvement we and others were installing, so you get a bit below this value to a few hundred femtotesla per square root of Earth. You can compare this with silicon carbide, and I'm just highlighting this here because it's an upcoming sensor material where you achieve sensitivities on the order of a few picotesla, say 20 picotesla square root of Earth, with slightly larger ensembles. And the reason is that the decoherence time and the signal contrast is a bit lower in this material. But this is improved all the way along, and companies like Infineon, for example, and Bosch are now trying to make compact, actually chip-size sensors based on silicon carbide, where the target sensitivity is 10 picotesla square root of Earth. Very well. Let me show you one application example, which we and others are working on these days. So what I'm plotting here is actually the magnetic flux density of physiological, biophysiological, or neuromagnetic signals. And it is plotted, where you see here is microtesla, this Earth magnetic field down to femtosecond, and it is plotted as a function of frequency at which these signals occur. One very prominent biomagnetic field is the magnetic field of the heart, which reaches some 10 to 100 picotesla amplitude. And it occurs over a frequency range from a few hertz, as you know, to a few tens of hertz in a healthy heart, at least. Then we have muscles which generate large magnetic fields. So this red line is which separates classical magnetometer like flux gauge, magnetoelectric detectors, and so on. So from quantum sensors, which are, for example, optically pumped magnetometers or these kind of ND magnetometers. And quantum here means that they rely on quantum coherence to occur. And everything below this line obviously then requires this kind of sensors. And specifically, if you want to measure muscle signals or brain signals, right, then you would need sensitivities significantly below a picotesla squared of hertz. All right. So what we were trying to do, and Ron works with, who is now at the University of Maryland, was also trying and successfully doing this, is measuring actually the magnetic field of a neuron. And we were actually teaming up with a bio group in Australia. They work on animals like this. This is a frog. And what we were actually doing is we're doing experiments on the neuron, which is responsible for the leg movement of this frog. And that's what you can see here. So this grayish thing, this grayish strip-like thing you see here, that's actually the neuron. You see an electrode here and here, which is actually meant to excite an action potential in the neuron. You see all of this being mounted on a cover slip, and what you cannot see or hardly see is actually the diamond underneath here. This is the microscope objective used to excite and read out NV centers in the diamond. And here we use the fact that with the NV center and with the diamond, you can come very close to the neuron, a few micrometer distance, which is very hard for any other type of sensor, including squid or atom vapor magnetometry. This is why there is really very little, if any, magnetometry experiments on individual neurons before these experiments. And what you see here is the result of such an experiment. So you see here the axon magnetic field. This is actually a misprint. It's not nanotesla, but picotesla. The magnetic field amplitude we measure here is up to 20 picotesla. And the temporal response, so the signal shape you see here is very typical for action potentials, which actually have this positive and negative sign, which actually mimics or is an indication of the physiological process underlying these action potentials. What happens when you actually excite these neurons with an electric field pulse is that you depolarize the membrane of this neuron, which means that there are membrane channels opening. And this leads to a current of certain ions. And this current, of course, generates a magnetic field. And this is why you see this magnetic field. And this current, as the pulse propagates across the neuron, is also changing sign. So you see an in and an out flux of ion. And when you see these kind of signals, you can be very confident that you actually see the magnetic field. And once again, I'm sorry for the misprint here. This could be picotesla. So the amplitudes you see are on the order of 20 picotesla, which is very much what you expect. And this is also requires you essentially to have this picotesla type of sensitivities to see the signal. And once again, I would not, there is only very few experiments, if any, which other than this type of system, which would allow you to do and record these single neuron signals. All right, of course, you get more ambitious, and this is what people are after now, and try to measure the magnetic field of actually brain activities. typically these days, this is done on squid. Once again, there is a misprint here on squid-based magnetoencephalography systems, MEG systems. Squids are superconducting quantum interference devices which comprise closed junctions. And to make these systems superconducting, you need to cool them down. This is why you need a big helium tank, and actually your subject sitting or sticking his or her head into that helium tank where a squid helmet is. The magnetic fields you expect are on the order of femtotesla, maybe at 10 femtotesla, also at a frequency range from very low frequencies, few hertz, to up to a few hundred hertz. And there is a fantastic new tool besides squids being able to do this. These are atom vapor magnetometers, and there is a lot of people who worked on the integration of these atom vapor type sensors into microscopic or at least, centimeter scale systems. I got this image here from Svenja Knappe, who is one of the, people who pushed this, and now also has a company commercializing that system. So in these systems, which once again is centimeter size, you achieve, say, 50 to 10 femtotesla per hertz, depending on the type of sensor you're using. And actually, the introduction of these atom vapor magnetometers into the MEG field is about to change, a massive change in the field. So people now can wear actually the sensors on their head. They can be fixed by a helmet, and this allows the subject to move, for example, play ball here. And that is a massive change, because for precise localization, you need these sensors to be in registry with the specific brain part. And there is a very nice paper here from a couple of years back from University College of London and QSpin, which is one of the commercial vendors selling these atom vapor magnetometers. So then that's a massive step forward, if not a breakthrough in this field. One thing we should not forget is that this technology requires shielding. The dynamic range of these sensors is on the order of nanotesla or so, or even below. And if in your lecture hall, for example, or here in my office, typically magnetic field amplitude due to ceiling lights or the vents in my laptop or so are more on the order of 10 to 100 nanotesla. So it's very hard to operate these sensors, if not, it's impossible actually to operate them in an everyday environment. And this is why the next step, and this is what we are doing now, is we are developing gradiometers, which are not based on atom vapors, but which are based on diamond sensors, where you have one sensor close to the source you want to measure, and one sensor a few centimeters away, which measures the background magnetic field, and then you operate them in a gradiometry type of way. What you need is a sensitive sensor for this, but you also need one which has a high dynamic range. And the dynamic range of these diamond and silicon carbide and solid state based sensors is way higher than in atom vapors, because you only have linear Zeeman shift to occur, whereas in the atom vapor, you have this quadratic Zeeman shift for low magnetic field, and this limits the dynamic range. In any case, so what we achieve these days in these gradiometers, and that's what you see here. So I plot magnetic field spectrum in Tesla per square root of hertz, going from nanotesla to picotesla. We operate these gradiometers, and what you see, what I plot here actually is the sensitivity curve of this gradiometer as a function of frequency of the magnetic field you want to measure for two channels we were employing. So this is the blue channel, one channel, and this is the second channel. And so the overall gradiometer, which subtracts the two channels, achieves a sensitivity of a few picotesla square root of hertz. And now we are trying to push this towards the, say, 200 femtotesla level sensitivity. And because of the large dynamic range, actually you achieve a sensitivity in an almost ordinary environment like an office space or a lecture hall. All right. And one key feature to achieve this is actually that our sensor sizes are getting small. So here you see a rather new compact version of these. This is a diamond sensor where the diamond is somewhere in between here. You see a mounting plate and a bit of an electronics component here. And the one thing you would need in addition to what is already in here is actually microwave, and it has the size of 1 eurocent. And you can shrink this down if you put a bit more sophisticated optics also down to 1/10 of that size. And this allows you really to do point-wise measurements at the site you're interested in here, this reddish site, or a few centimeters away. All right. So with that, I would like to switch gears, and for the rest of the talk, rather talk about micro to nanoscale sensing rather than large sensing volumes. And one way to go towards nanoscale sensing is actually use single defects or single dopants and scan them across the specimen one is interested in. And one device which allows you to do this, you see here on this transparency. So what you see here, this brownish thing, is a diamond plate. And you see a small protrusion here at the end. This is essentially a diamond waveguide. The diameter here is below a micrometer. Well, you see the length scale here. And at the end, I was PowerPointing a red dot. This is actually where a single defect is sitting. And this diamond plate is mounted here on a stylus, and you can move it across the surface. It very much works like an atomic force microscope, if you like. And while moving, you can excite and read out actually the response of the defect by shining a laser here from top and collecting fluorescence at the top. These, well, one thing I should mention, these structures here, you can buy these days. There is a couple of startups which actually sell you these products, and this is actually how we do it. In the old days, we were doing these structures by ourselves, but now we buy them from companies, and it's getting a standard tool in a lot of areas in biophysics or material science. And I would like just to highlight you one example. I would give you one experiment which we're doing together with a group at USTC in Hefei, China, a couple of years back. So we were taking one of these tips and this structure here to symbolize one of these tips, which you can move laterally, but also so you can move it horizontally, but also vertically. And what we wanted to measure actually is the presence of an electron spin on a protein. You can operate these systems at room temperature. You can operate them under physiological conditions, so you can stick them into a buffer or a water solution, which keeps this protein happy. This protein is an MAD protein, and it plays a role in cell mitosis, so it regulates mitosis. The protein in itself is diamagnetic, so it contains no electron spins. The only source of magnetic field would be the nuclear spins, like protons or carbons, but these ones we were not measuring at this experiment. So if you want to make this detectable by your sensor, you would need to put an electron spin. And this is what people do in biochemistry rather routinely. You can take a small molecule here. This is a nitroxide radical. Nitroxide comes from the nitrogen, which is otherwise in a carbon environment. And this has a dangling bond. And in this dangling bond, so unpaired or unbonded molecular orbital, there is a single electron residing. And then once again, that's standard in biochemistry. And then you can measure the interaction between this electron spin here and electron spin here. They make dipole-dipole interaction. In other words, you can measure the magnetic field of that electron spin here at this point in your tip. And the result you see here, so we were putting these proteins on the surface. They like to stick on the surface because they have Coulomb interaction. And then you scan across the surface with this structure here, and you see all of these blobs here, and every blob marks the position where the interaction, the magnetic field at the surface is particularly large. And well, our interpretation is that these are individual proteins with single of these electron spins. The scale by here is 100 nanometers. That gives you roughly an idea on the spatial resolution. So you can use that structure, this technique, actually to localize these electron spins. But you can do more than this, and this is what I would like to allude to. I was already saying that these NV centers and most defects in solids are vector magnetometers, which means you can not only measure the strength of a magnetic field, but you can also measure its orientation. And this comes from the fact that the electron spin is pinned by a crystal field, which is given by the structure of, in this case, of the diamond. And so you can, for example, measure this angle theta. And that's what I'm showing you here. And I'm not going into details because one would need to interpret these spectra you see here in detail, but just to give you an idea on the principal idea of the technique. So this angle theta here is not isotropically distributed, but because of spherical hindrance, this molecule can only take certain orientations. And essentially what you see here is a histogram of these possible orientations. It is imprinted in interaction, or encoded here in interaction frequency, but well, this is how you could read it. And we were doing these experiments, and we were measuring the interaction, this interaction histogram, and then fitting it to different ways on how this electron spin can move. And the best fit here is given by this red curve. And this red curve tells you that over the course of the experiment, so it roughly takes you about a minute or so to measure each of these points. So over the course of doing all of these experiments here, this angle theta was actually changing on average by a factor by 25 degrees. And this change actually of this angle theta mostly comes from the flexibility of the subpart of the protein this electron spin is fastened to. So in essence, or the punchline is that with this technique, you can measure local protein mobility. And this local protein mobility then goes into a mathematical model of the overall protein function and mobility and provides valuable insight into what you're looking at. And I would not know of any other methods being able to do this on an individual protein level. Of course, there is ensemble methods which describe average behavior, but this one is really done on single proteins. All right. So, well, as I was maybe going back here, as I was saying, actually to measure this, you need this extra electron spin. On the other hand, you could ask yourself, well, and that's what I was already mentioning, there is an intrinsic magnetism coming from the nuclear spins in this protein. Would you be able to detect this magnetic field with this sensor also? And the answer is affirmative, of course, otherwise I would not bring up the topic, but now I tell you how we do this and where the challenges and pros and cons are compared to measuring electron spin. All right. So nuclear magnetic spins have a magnetic moment, which is roughly a factor of 1,000 smaller than electron spins. So being able to measure this is a step, would require a step ahead in sensitivity. And the sensitivity gain we employ here, we brought about here, comes from the fact that we are not measuring DC magnetic fields, but we generate a frequency selective magnetometer. And the way we do this is described in this transparency. So if you put a nuclear spin, say a proton spin, into an external magnetic field, of course, it starts to precess because it has an angular momentum and it has a magnetic moment. And this precision frequency is a Larmor frequency. It depends on the nuclear G factor to begin with. And so when you have a magnetic field, you exactly know at which frequency you expect this Larmor precession. And we specifically pick up magnetic fields at a very specific frequency. And the way we do this is rather than, just measuring the Rabi oscillation or the Larmor precession with a broadband magnetometer, we invert the electron spin of the magnetometer periodically. So we apply a pi pulse or a NOT gate every now and then with a spacing of tau to the electron sensor spin. And we do this exactly in registry, so commensurate with the oscillation of the magnetic field of the nuclear spin. If you do this, then essentially what you do is, if you look at the response of the accumulated phase of the sensor, you rectify the oscillation of the Larmor signal of the nuclear spin. So in a more quantitative way, this is like using a local oscillator in your old analog radio, or like using a local oscillator in your lock-in amplifier, right? It's exactly the same functionality. And because we can change tau quite easily, technically, we can actually scan across a certain frequency range and pick up the magnetic field specifically at that frequency range. And that's how we do it. So essentially what we measure is we measure a magnetic field component, say, along BZ, which is modulated with the Larmor frequency of the specimen or of the nuclear species we are interested in. And here you see such an experiment. So on the one hand, what I plot here on the y-axis is essentially the time-varying magnetic field. This is why it does not say magnetic field, but S of B as a function of omega. But you can forget about that, right? It's once again, the unit is nanosecond square root of hertz. And now I plot it as a function of frequency, which essentially is 1 over the pulse spacing of the pi pulses I apply to my sensor. And it is centered to the Larmor frequency I expect for proton spins. Let me show you this. So specifically, the experiment is done such that we take NV centers. This is now not scanning at the moment, but it's just one of these NV centers very close to the surface, few nanometers. You put a drop of liquid on top of it, say water, and then exactly you do this magnetometry scheme. You change your tau, that is, you change your sensing frequency, and lo and behold, at the frequency of the Larmor precession of proton spins, you see a signal. This can be water, it can be oil, which is not evaporating that fast. This is technically, it's a bit easier, but it's just a proton hydrogen-containing liquid. You can do this also with a solid. PMMA is polymethyl methacrylate. That's a polymer which also contains protons. You see the same type of signal, but you can deuterate that specimen, and then the signal disappears. So that gives you pretty good confidence that you really see a proton Larmor precession modulated magnetic field. The root mean square amplitude of the field is not small, right? It's almost half a microtesla. Distance between the spin here and the spin here is on the order of say 6 nanometers or so, 6-7 nanometers. And the signal, the effective signal, comes from roughly 100 proton spins out of a detection volume of 10 to the 5 5 nanometer cube. Right. So it's a rather sizable signal from a small number of proton spins, which one is able to detect because you can go close to the source of the signal. So it's a proximity sensor. And we did this now almost, exactly 10 years ago. And in the meantime, people have very much worked on improving the sensitivity. And there is now experiments on single nuclear spins where people really see the, magnetic resonance or NMR signal of single proton and carbon spins and so on and so forth. So this is now, it has matured and developed into a technique where people try really to do this for chemical structure analysis. All right. So actually the machines we are competing with are standard machines measuring nuclear magnetism. And this is these nuclear magnetic resonance machines you see here. These machines are going to ever larger magnetic fields for two reasons. One is sensitivity, because the sensitivity scales with the Larmor precession of the nuclear spin square. And in these big machines here, which almost go to 1 Tesla of an external magnetic field, 800 megahertz to be specific, you have a sensitivity of 10 to the 13 to 10 to the 15 nuclear spins. Our system is way easier, so it's way more compact. It's actually a very simple setup. The sensitivity we get is easily 13 orders of magnitude better, right? There is no comparison in terms of sensitivity. I don't know about Bengaluru, but I'm pretty sure that other universities in India have multiple of these machines because they are toys for where they are the #1 analysis. Well, not the #1, but they are one of the most important machines to analyze bio structures. And the reason is not their sensitivity, right? This is obviously bad, but the reason is their spectral resolution. So what you see here is the NMR spectrum. So these are all the Larmor frequencies such a spectrometer picks up from carbon-13 nuclei in say, a typical, say, ubiquitin or so of a protein. And what you see on the first impression is that it's not just a single peak, but it's multiple peaks. So although all of this is carbon-13 nuclear spin, so by the G factor, they all should fall to 1 frequency, but that's not the case. Actually, they have a wealth of frequencies. And the frequency axis here is quite remarkable. It's called chemical shift, and it's ppm, so parts per million. So this is actually a fractional shift of the Larmor frequency from the pure G factor value or from some reference. Parts per million, so the Larmor frequency here is on the order of 40 megahertz or so, or 100 megahertz. So parts per million means that this is a frequency axis in hertz, right? So what you need actually, and this is why our colleagues in biochemistry and chemistry use these machines, is you need hertz resolution to see all of these tiny differences. Now, as a side remark, why do we have these multiple frequencies here? Well, these multiple frequencies come from the fact that the nucleus is seeing a chemical shift, and the chemical shift actually is a diamagnetic screening effect. The electron, the electronic wave function surrounding the nuclear spin is trying to diamagnetically shield the nuclear spins from the external magnetic field. So even though you only have, all of the orbitals are occupied, so you have pairs of electrons, no paramagnetism, you have a diamagnetism, and this diamagnetism in the molecule depends on the local electron density, which is unevenly distributed across the molecule. And so essentially what you measure here is local electron density, and this local electron density directly relates to molecular wave function, and this directly gives you access to structure information. And there is rich structure information, that's what you see here. Now, if you come along with a new method, what you obviously need to show is that besides an increase in sensitivity, which is massive in our case, you also need to have this kind of spectral resolution. Okay, so let's go through this. So typically, by the way, these machines operate, and this was Nobel Prize awarded like 30 years back, is that you record an FID. So what you do is you apply a microwave pulse. All of the nuclear spin starts to process each at its individual frequency. You record this oscillating magnetic field, and then you do a Fourier transformation, and you come up with a spectrum. This is how these machines operate. Right, that's a time-efficient way of doing these experiments. All right, now let's see if we can do something similar. And well, maybe I go 2 slides back to highlight the problem. Well, if you look at our spectra here, this is exactly, we are measuring Larmor precession, so it's exactly like the classical NMR, nuclear magnetic resonance spectrometer, is operating. If you look at the line width here, you see that this scale is kilohertz. So the line width here is on the order of a few kilohertz. And why is this so? The reason is that the relaxation time of the sensor electron spin is on the order of milliseconds, right? This is the T1 time or the T2 time we had. It is limited at room temperature. If you want to stay at room temperature, it's limited to milliseconds, and that means kilohertz, which essentially means that the local oscillator we are using has a frequency width of a kilohertz, and so you will never be able to resolve hertz signals, because your signal is always a convolution of your local oscillator signal and the external signal. And your local oscillator signal is a kilohertz wide. You never see hertz lines. So it's an intrinsic problem of the sensor that we are not able to achieve hertz line width to begin with. Now, and here comes now a trick I would like to show you, and with this I will start to conclude the talk to leave some time for discussion. So if you use the electron spin alone, you will not achieve this kind of spectral resolution. But if you employ a memory spin in addition, you would be able to do it. And I will show you how these memory spins look like. Now, the overall sequence looks like this. It's a wire diagram. Some of you might know from quantum information processing, but I'm going to walk you through this step by step. So what we do is we use, and as you will see, we use carbon-13 nuclear spins, which are in the diamond as memory spins, and we use the electron spin as sensor spin. First thing is we apply a pi/2 pulse to the nuclear spin, or it's a Hadamard gate if you like, and then we apply a conditional NOT gate, which is a pi pulse, the result of which depends on the quantum state the nuclear spin is in. And these 2 pulses generate an entangled state among the electron and nuclear spin. And I'm giving you this in this kind of quantum information type of notation. In the beginning of the experiment, I should say we initialize the electron spin in one spin state, which we symbolize 0, and we initialize the nuclear spin. We can do this ancilla nuclear spin in one spin state, which is 1. By these 2 pulses, you generate this entangled state. Now you let this entangled state to interact with the magnetic field you want to measure. This is what is called phase accumulation. And then this state generates, well, it picks up a phase, right? Then you apply another pi/2 pulse, which is a conditional rotation of the electron spin, or a C0 gate, to disentangle electron and nuclear spin state. So you factorize out the electron state, which is state 1 in this case, and this would be the state of the nuclear spin memory. Once again, I have not shown you what the nuclear spin memory is, but I'm going to show you in a second. And this state, now this overall state, you let evolve for a time capital T with the external magnetic field. Okay. And then you apply the same sequence, you essentially revert the pulse sequence. Because during this time capital T, the electron spin is one of its eigenstates, it does not accumulate a phase. and the nuclear spin in itself has a factor of 1,000 smaller magnetic field. It will not interact very much with the external magnetic field. So essentially, this is a kind of a correlation sequence, very much. So it's just a bit more complex than like the classical Rabi pi/2 correlation measurement. So essentially, what you do is you measure a certain phase phi here, and after some time capital T, you measure the phase difference your system had between this time and this time, right? This is why the delta phi here occurs. But the delta phi is exclusively in your nuclear spin memory, and you need to retrieve it to the electron spin, and we know how to do this. And by this, you extend your interaction time to capital T. Your electron spin dephasing time does not play a role anymore in the overall business, but it's only the nuclear spin memory relaxation and dephasing time determining your spectral resolution, which is way longer. It is seconds, and this is how you achieve Hertz resolution. One remark to these nuclear spin memories. Up to now, we were only talking about the electron spin, doing any measurement. But this electron spin is living in a diamond, and if you do not isotopically purify the diamond, with 1% probability, you find a carbon-13 nuclear spin in the surrounding, right? You can isolate these, or you can measure the hyperfine coupling of this electron spin to these nuclear spins. Typically, they are on the order of a few megahertz down to a few kilohertz, depending on the distance. So mostly it is dipole-dipole interaction. The further out you go, the stronger, the less strong the interaction is. And here you see a hyperfine spectrum, right? From a few kilohertz to a few 10 kilohertz. The good thing is that the relaxation time of these nuclear spins, and this is what is important here, at the magnetic field of 3 Tesla and at room temperature is on the order of 4 minutes or so. And this T1 is ultimately limiting your spectral resolution. So if you employ this quantum memory trick and this entangled, disentangled type of correlation experiment, you really gain massively in spectral resolution. And we were showing this like, it's almost now 6 years ago. So we were taking a single electron spin together with a quantum memory. We were measuring the NMR signal, so the Lama oscillation of different nuclear spins in this molecule. It's a perfluoro polyether. The important thing is that we use the fluorine nuclear spins, which actually have 2 different frequencies. Although all of this is fluorine, this pinkish guy here has a different frequency than the other ones because of the chemical shift. And if you do this quantum memory entanglement assisted scheme, you see that you start to see the 2 frequencies here. The spectral resolution is on the order of 200 hertz, so it's not the hertz you would like to have, but this is just a demonstration experiment, and people really have increased spectral resolution these days to hertz level. And the important thing is you see these 2 signals here, which indicate that you can see this chemical shift. You can compare it with classical NMR. These are the solid lines here, and you see that the measurement with a quantum sensor exactly reproduces this result. The detection volume here is some 10 nanometer cube. So the number of nuclear spins we are measuring is 10 to the 6 and not 10 to the 2. This was one of the compromises we were working. But at least this shows you that the system works and that our sensor is able to do Hertz resolution. I would like to, and maybe by this I call it, I stop my presentation. I would like to point out, if I go back, that typically we have not only a single nuclear memory, but we have a whole list of nuclear memory quantum bits, up to 6 or 7. So we can not only employ a single nuclear spin as a quantum memory, but we can use a whole bunch of them. and then apply a gate sequence like this. And for those of you who were teaching quantum information processing, or who attended a lecture, or who were reading books and listened to talk, this kind of gate sequence where you have these kind of conditional rotations with specific angles, that if you have seen this, that is nothing but a quantum Fourier transformation. So with multiple nuclear spins, you can not only measure a single frequency, but you can encode multiple frequencies you measure in your signal in multiple nuclear quantum memories, and by this do an online or an onboard quantum Fourier transformation. We did this, but because I want to leave some time for questions, we'll deal with this my next lecture. So, okay, so I sum up. I haven't made it through all of the list. The rest is coming, but what I want to, the gist of my talk is that these spin defects in solids are a very versatile quantum sensors. I believe their strength is not so much in competing with the very high sensitivity sensors which are already out there, fantastic technology, but rather with the small length scale, you can apply these sensors too. You can measure various properties, and once again, next time I'll show you how to measure a temperature, or for example, also local viscosity. The sensitivity we reach is slightly below a picotesla. You can convert this into an imaging device. This is also something I will show you on Wednesday. And you can employ additional degrees of freedom, like nuclear memory, quantum bits, which, for example, give you a massive increase in spectral resolution. Very well. So, and another thing is that this is now coming towards device fabrication. 10 years back, our lab, would look like this, but now we gradually start to make these sensors, we and others, and industry companies, I should say, make these sensors more and more compact, down to 10 type of sensors, which have good sensitivity. Okay, so these are the folks in the lab, whom I thank for all of the various contributions to the experiment. We have collaboration all across the world, and we get money from different sources. I thank those people for your attention, and I thank you also for your patience. And once again, I'm happy to answer questions you might have. Thank you.
Thank you, Professor Jörg. So floor is open for questions. Any questions? No questions? Okay, Professor Jörg, I'll start with questions.
Okay.
So couple of questions that I have. The first question is for the small compact sensors that you have. What is the optical power that one needs to really reach this sort of sensitivity in terms of picotesla? And how do you handle the thermal issues with this?
Yes. So in this system here, and in this system, we roughly have 100 milliwatts, 50 to 100 milliwatts. And indeed, getting away the heat, having thermal heat sinks is a point. And this is why here in this case, you see this metal plate beneath that is actually a heat spreader we use here. I guess if you compare this to atom vapor magnetometers, indeed the optical powers are way higher. But the key achievement here, or the key parameter you need to work on, is actually the efficiency by which you excite. And if you do this very efficiently, you can reduce the optical power significantly below 100 milliwatts. But I guess it will be somewhere from 10 to some, say, 50 or 30 milliwatts is what you will need for reaching picotesla sensitivity.
So in this case, this is free space, or you have like a fiber coupled input as well to the?
Yes, no, this is not free space. It's a waveguide coupled, right? It's not really a fiber, but we have a more of a custom design waveguide, which is a coupling from, this is an LED, by the way, from the LED in an optimum way to the diamond. And then the optics is optimized, and then the diamond has a specific shape, and it has a reflective plane on it. And if you actually optimize what people call the entendu, which is numerical aperture and area over which you excite, if you optimize this carefully, then you significantly go down below 50 milliwatts of power required.
Okay. Yeah, so that is one question that I had. And the second question I have is more sort of general. So here you used the nuclear spin memory as a sort of a way to really use the quantumness of the system to get to better sensitivities and better resolution. But what about the other angle where people have been talking about, using cavities? What is your take on that approach? And do you think that will be really ever be possible to reach, beyond the standard quantum limit with using the cavity ensemble spin effect?
Yeah. Well, I guess what we are limited with these days is in our ensemble sensors is the dipolar interaction among the spins. So our ensembles are so dense that dipolar interaction is starting to play an important role in determining the dynamics. So if you carefully look into actually the evolution of the system, you see that due to dipolar interaction, entangled space starts to build up. So one of the knobs to increase sensitivity, obviously, at a given volume is to increase the concentration. And if you further increase it, say by a factor of 3 or 4, you would see that you have, rather than, than looking at the system as individual particles, you will have dipolar interacting spins to be the quantum system you want to study. And along those lines, complex quantum dynamics and finding methods on how to actually isolate the specific target state to measure actually your external parameters is going to be the key challenge. And I believe that along those lines, we will see that the standard quantum limit, or at least any kind of deviation from the standard quantum limit, is going to occur. And because dipolar interaction is long range, right, and you have it in 3D, you can have it in 2D, the kind of changing the effective interaction physics, in a sense that you average out dipolar interaction along certain directions. This is going to be what I guess we and others will do in the coming years. With cavities, sure. I mean, these are, if you speak about optical cavities, then this is a fundamentally different way to go, because here I've talked about room temperature experiments where actually the phonon-induced relaxation of optical transitions give you picohertz coherence times, and then generating, a strongly coupled system with a cavity is not very easy. You could do this with microwave cavities, that's true. And people start to do this. There is this maser type of activities where the stimulated emission is playing a role. So in that regime, yes, you can research on increasing sensitivity or deviate from standard quantum limit.
Yeah. So yeah, we have one question from the audience. Just use the.
Sir, you have said that it is calibration-free magnetic field measurement, because you said that G's doesn't depend on the environment, but G I think it depends on the spin value. What is the value around it? So it will depend on the spin environment of the defect. How it is then calibration free of
Yeah.
the.
Oh, okay. Yeah. Well, I guess I was careful in not saying not that it's entirely calibration free, but quasi calibration free. Indeed, the G factor of NV and other spins in solid is not precisely the free electron Z factor, right? But it depends on the crystal field, and so there is a certain heterogeneity. But this heterogeneity and deviation typically is smaller than the typical resolution we have. So given the sensitivity / resolution we have, these at the moment from these sensors, Z factor heterogeneities do not play a really a leading order. But you're right, these are not atoms. They are not free atoms in a gas, in a diluted gas, but they are dopants in a solid. So in principle, you would need to know this. But answer is, at the moment, our precision is not good enough to see these differences.
Okay, thank you. Any other questions? Anybody has? Okay, if not, thank you, Professor Wrachtrup, for this fantastic talk. We look forward to your next talk as well. Thank you.
Okay, see you then. Bye.